This is lecture number 4 in the heart or cardiovascular series. And learning objective number 1 is, why do we need electrical activity of the heart? Because really, this whole lecture is really going to consider electrical activity of the heart. It's not going to go super in depth. We'll save some of the detail for later lectures, but we're going to give a broad overview here. So why do we need electrical activity of the heart? In the first place, describe the patterns of electrical activity of the heart. And then name the autorhythmic cells and which one of those is called the pacemaker. So let's answer number 1 first. Well, if we wanted to say it very, very simply, why do we need electrical activity in the heart? Well, we need electrical activity in the heart for the same reasons that we needed electrical activity in skeletal muscles. And if you go back to what you already know about skeletal muscles, you know that there is this broad principle called excitation-contraction coupling, which really talked about how do we take an electrical signal, that action potential, and convert that into the mechanical pull that we see in the sarcomeres. So heart is just a muscle, right? It's just, and when I say just a muscle, I don't mean to overly simplify it, but what I do want to do is I want to draw a connection to what it is that you already know about how sarcomeres work, right? You needed that action potential generated at the motor end plate, traveling through the sarcolemma, going down the T-tubule, eventually opening up calcium gates at the sarcoplasmic reticulum, and that was that nexus point, right? Where the electrical signal then all of a sudden would lead to that mechanical pull through another series of events. Well, it's no different here. We must have electrical activity because you've got to depolarize before you lead to contractile activity. So let's go to this slide. The heart has electrical activity. It starts in one specific place and then spreads to the rest of the heart. We're going to look at that. Where is that electrical signal actually generated, and how does it spread to the rest of the heart? So it's a little bit different, but kind of conceptually the same as what you already know about an action potential. An action potential is generated at one point on the skeletal muscle, and then a wave of depolarization spread throughout the sarcolemma. Well, from a certain point of view, it's the same thing here. You're going to see an electrical signal begin at one place in the heart, and a wave of depolarization is going to spread through the rest of the cardiac muscle fibers. So same kind of concept. Remember that you must depolarize before you can contract. Depolarization comes before contraction. The electrical event occurs before the contractile event. Okay? Before the light bulb lights up, you gotta send juice to it. You gotta send electrical signal to it. So this is a very sequential process. Depolarization comes before, and they're directly related to one another. Without depolarization, you will never, ever, ever see contraction of any kind of muscle. And so it's a useful time for you to go ahead and review action potentials. If you've forgotten some of the details, then it's a useful time, like I said, to go back and look at action potentials, because we will look at action potentials here in the heart in a later lecture. But when we do that, we're really going to just build upon your pre-existing knowledge of action potentials and just make a couple very important changes with respect to the heart. So let's look at this picture. Electrical conduction starts at this place called the SA node. What is the SA node? It's just an area of the heart where you've got some specialized muscle fibers, and this is where the electrical signal is going to originate. So here's the thing. For right now, I want you to put on hold this idea of, well, what do you mean the electrical signal originates there? Like it just magically generates an electrical signal? And you know what, for right now, that's fine. Let's call it magic. For right now, there's just kooky stuff that happens at the SA node where it spontaneously generates its own electrical signal. Now, this is where we depart from skeletal muscle, right? In skeletal muscle, where did the electrical signal get generated? At the motor end plate. But it didn't do it on its own. It did it as a direct result of neurotransmitters coming from nerves, right, crossing that synapse. That the nerve signals themselves are what allowed that motor end plate to generate the electrical signal. But here, it really is going to be independent, spontaneous, magical. Again, magical for now until we understand some of the details later. So in any case, if you want to know how the SA node generates its own signal, it says here, SA node generates impulse. How does that happen? For now, let's just shelve that thought. Let's just learn SA node generates the impulse somehow. The somehow we'll get to later. Now, what happens from there? Well, once you start from there, atrial excitation begins. Now, remember that the atria are right here and the ventricles are here. And what we're going to start to see is a wave of depolarization, action potential spreading throughout the entire atrial myocardium. And so that's what we're seeing here. So what we're going to see, though, is that as that wave of depolarization spreads throughout that atrial myocardium, eventually that signal seems to kind of almost die everywhere, and it gets held momentarily here at this area called the AV node. So you see here in the text, impulse is delayed at the AV node. What happens after that? I'll talk more about that a little bit later. From there, the AV node, it just kind of delays that signal just a little bit. You can imagine, these movie scenes where like there's the good guy chasing after the bad guy through a crowded marketplace, and the bad guy all of a sudden starts tossing like vegetable stands over just to get in the way of the good guy chasing after him. And so, when he tosses over vegetable stands and chairs and tables, he's not really expecting the police officer or the good guy in pursuit to stop. He's expecting simply to slow him down. So similarly here, the AV node's job here is to slow down depolarization. Well, what does that mean? It's going to slow down depolarization of the ventricles. So what we don't want to see, we don't want to see the atria depolarize and the ventricle depolarize immediately after. We want there to be just a little bit of lag time. And why do we need that little bit of lag time? That little bit of lag time gives time for blood to fill the ventricles before the ventricles will contract. So the job of the AV node is very, very important. In any case, after the AV node allows that electrical excitation to pass through, it travels through these things right over here called the bundle branches. These things right over here are called the bundle branches. And so actually before the bundle branches, this section here, which is unlabeled, is called the AV bundle. So if you come right over here, it's the same thing, same theme, just a different image. There's the SA node, wave of depolarization spreads throughout both the right and left atria. That signal then is held at the AV node just for a moment. And then that signal travels through the AV bundle, the atrioventricular bundle. And then from there, that bundle is going to bifurcate. It's going to split off into bundle branches. We have a left and right bundle branch. And these bundle branches are going to go to the left and right sides of the heart, the ventricles, respectively. So that's what we're looking at here. The bundle branches are coming down here, and we can see that that right bundle branch is going to lead to depolarization of that right ventricle. The left bundle branch is going to lead to depolarization of the left ventricle. There definitely is going to be overlap. However, just to keep life real simple, we're going to say left bundle branch to left ventricle, right bundle branch to the right ventricle. All right? And so then the other thing that you want to notice here is that how does the atria depolarize? And what I mean by that is this. I know that's a very vague question. If I were to make it multiple choice and say, how does the atria depolarize? Does it go A, from top to bottom, or B, from bottom to top? You would say, well, it kind of looks like the AV node is closer to the top of the heart, the base of the heart, and that wave of depolarization then goes from top to the bottom. Yeah, and you'd be right. What about the ventricles? How do the ventricles depolarize? The ventricles actually depolarize from the apex, right over here, the apex of the heart, upward. And now, if that seems a little backwards to you, understand that this is useful for us, because when we take a better look at that, remember that all these valves are essentially lined up in the same plane. Okay, they're not exactly the same plane, but if you squint at it and functionally, they're essentially in the same plane. So what that means then is that if you had depolarization that occurred from this section here all the way down, meaning if it started at the top of the ventricles and went down, then we're kind of pushing blood kind of in the wrong direction, right? You're still going to get some ventricular ejection without a doubt, but it's just less efficient as compared to squeezing from this way on up. You might liken this to those of you who are very particular about squeezing a tube of toothpaste from the bottom and rolling it on as you go up towards the top, compared to people that just squeeze right in the middle. Okay, so for those of you who squeeze from the bottom and roll all the way up, like the instructions say, well, that you do that for the very same reason that the ventricles are going to depolarize from the bottom or the apex, then onward to the top. All right, so this is that wave of ventricular depolarization. What you see here at the bottom are the EKG signals. We've got some separate slides down the road to talk about EKG signals, but what I want you to see is that when you look at these things, these different waves in the EKG signal, the signal itself is simply indicating electrical activity of the heart. It is not measuring contractile activity of the heart. One more time, the electrocardiogram, the EKG, measures electrical activity of the heart. It doesn't measure contractile activity of the heart. Now, it is a pretty safe assumption, though, to say that if the electrical activity of the heart is okay, then the contractile activity of the heart is probably going to be reasonably okay. In other words, the thing that tends to be kind of the deal breaker between, if you think of the heart as electrical activity and contractile activity, just like we thought of skeletal muscle, when things go wrong, what kinds of things are more likely? Contractile problems or electrical problems? And I'm going to tell you electrical problems are just going to be more common than contractile problems are going to be. All right? Okay, so now we've got kind of our general pattern of depolarization. I want to talk a little bit more about the SA node and AV node. When you look at the SA node and AV node, these are considered to be autorhythmic cells. And what that means in English is that they have the ability to magically, again, and it's not really magic, but I'm just using that term, magically, spontaneously generate their own electrical signal. They have the ability to generate their own independent action potential, which is crazy because we've never seen that before. We didn't see that in the nervous system. Well, it depends where and how you study the nervous system. As a general rule, we don't see that in the nervous system. There definitely are exceptions to that, some areas that are even referred to as pacemakers of the nervous system or of the central nervous system. So those cells do exist. I don't typically bring up those cells in an introductory A&P course. So in any case, for all intents and purposes, we've not really seen this ability for electrically excitable tissue to generate its own signal. We've always seen it come from somewhere else. And so this is where autorhythmic cells are weird, man, and they're just funky and very unique in that regard. So SA node here, sinoatrial node, we already seen him. We've seen the atrioventricular node as well too. We saw the AV bundle, and the Purkinje fibers I didn't specifically call out, did I? These are the Purkinje fibers here. So in other words, as the bundle branches come down, once they make that turn at the apex, we're just going to rename them Purkinje fibers. So there's Purkinje fibers also have some autorhythmic possibilities. Potential, I think is what I mean. So the SA node, left to its own devices, right? If you just let the SA node run, doing its own thing without any kind of interference, what is its rate of depolarization? The rate of depolarization, although the estimates can vary, is anywhere between 80 and 110. So that is 80 to 110 depolarizations per minute. So stop for a second right now before I go on. Think to yourself, hang on, what is resting heart rate? My resting heart rate is, let's say 60 to 80 beats per minute, right? In that ballpark, maybe 70 beats per minute, something like that. But what I'm telling you right now is that the default, left to its own devices, without any additional, neuro or endocrine interference of any kind, the SA node will run at 80 to 110 BPM. I shouldn't say BPM. It's not a beat. It's number of depolarizations per minute. AV bundle will run at 40 to 60 depolarizations per minute. AV bundle is 20 to 40, and Purkinje fibers are 15 to 40 depolarizations per minute, left to their own devices. Now, in real life, though, of course, things are not left to their own devices. If you go back to what you know about the nervous system, you know that the heart itself is innervated. We're going to see that later on down the road. We'll see that sympathetic innervation. We'll see parasympathetic innervation as well, too. And so in real life, this idea of left to their own devices, it just doesn't ever exist in real life humans. But again, if left alone, if you were to denervate the heart, meaning clip the nerves that run there, these are the rates of depolarization. So why is the SA node then considered the pacemaker? What makes him the conductor that sets the pace of the heart? And the simplest answer is that, well, he's the fastest one. He's the fastest one. So what that means then, look, let's say just momentarily you were to turn off all these autorhythmic cells and you just took a needle to depolarize. What I mean by that is if you went right up here to the apex of the heart, could you make this heart depolarize backwards? Instead of going from top to apex, could you make it go from apex all the way to the top? Yeah, sure you could. Just like you can see retrograde electrical signals in neurons, you can see that kind of thing in heart as well too. Again, in a fake experimental situation. But why is the SA node considered the pacemaker? Because he's the fastest. So the SA node is sitting here going boom, 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 boom. And the rest of these guys, which are electrically excitable, have no choice but to follow suit. They just follow suit because they're all wired together, so to speak, right? They're all connected. And so when an electrical signal runs through them, they're going to depolarize because they have electrical excitability. So SA node is considered the pacemaker. Now, this brings us to a very interesting question then. And the interesting question is, let's just use the number 100, okay? Just to make the number simple. Let's say the SA node spontaneously depolarizes 100 depolarizations per minute. And we consider resting heart rate at 60 or 70 beats per minute. Well, that doesn't quite line up, right? Because the rate of depolarization of the SA node should be the same as the rate of the heart rate itself. And so what gives here? What does that mean? What that tells us is because the SA node runs at this speed, but we know resting heart rate is lower, it means that under resting condition, what is your physiology trying to say to the SA node? Specifically, what is the nervous system doing to the SA node? I'll make it very simple. Does it make it speed up? Does it encourage SA node to speed up and say, come on, give me more, give me more? Or is it encouraging SA node to hold back just a little bit, to chill out, to put the brakes on just a bit? And the answer is the parasympathetic nervous system is putting the brakes on the SA node constantly at rest. And when I say brakes, really, I'm talking about kind of a light brake here. I'm not talking slamming the brakes. If you slam the brakes, SA node doesn't work and you die. I'm talking about getting it from its normal native 80 depolarizations per minute to say, hey man, I need you to slow down to 60. And that happens under parasympathetic input, okay, typically from the vagus nerve. We'll look at some of that later on because I have some slides that show you the innervation of the heart, but I wanted to call that to your attention right now. Okay, so let's recap what we've done here in this lecture. Why do we need electrical activity of the heart? Like I said, for the same reason we need it in skeletal muscle. Describe the electroactivity. Well, it starts at the SA node. The AV node then holds that charge momentarily. It then passes through the AV bundle, right and left bundle branches, then the Purkinje fibers, leading to depolarization of the ventricles from bottom to top. Name the autorhythmic cells. There they are, SA node, AV bundle, Purkinje fibers, and the one that's considered the pacemaker of them all, the guy that sets the pace of the heart, is the SA node, the sinoatrial node. All right, that'll wrap it up for this lecture.